My name is Jelle. I am a Master of Logic student at the University of Amsterdam and the Institute for Logic, Language and Computation. In the spring of 2020, I wrote my bachelor thesis on capturing human-like biases in positive operators. It has been shown that distributional semantics is very good at capturing meaning based on some human curated corpus. However, it has also been shown, namely by the implicit association test, that humans exhibit some kind of implicit biases. And now, if it is the case that these implicit biases that humans possess, if they are actually also present in the corpus that, or the written data that they produce, is it then also the case that the machine learning methods in natural language processing that are based on these corpora, do they also express the same implicit biases that humans do? And it's exactly the word embedding association test by Katrin et al. In 2017 that showed that this is actually the case. They used the IAT as a reference and shown that the implicit associations that the implicit association test recognized are also present in distributional semantics, or word embeddings. And what my thesis did, or what I did in my thesis, is that I attempt to replicate the word embedding association test. However, I use a method that is more closely related to the methods that are used in the IAT, which the word embedding association test does not. What the IAT does, or the implicit association test, is that it has two sets of target words and two sets of attribute words, and it measures the response time that a certain human subject has when it tries to associate the word programmer with the word male, or the word programmer with the word female. And the null hypothesis that it uses to test for these implicit associations is that it supposes that there is no difference in the reaction time where it associates, where it reacts to the association between programmer and man, or programmer and woman. And similarly for nurse and man and nurse and woman. However, the implicit association test shows that humans actually do possess some implicit biases, and that they do react faster on, say, the test whether programmer is a man or a programmer is a woman. Namely, they show that, for instance, the word programmer is more associated with the word man, and the word nurse is more associated with the word woman. So the measure that they use is the response time in this categorization task. And as I said before, the null hypothesis is that there is no difference between the relative association between the two target sets and the attribute words. The word embedding association test can be seen as the NLP version of the IAT, and instead of using the words itself and the reaction time, it now uses word embeddings, a model of distributional semantics, namely the GLOVE, or the global vectors. And instead of measuring response time, it measures the cosine similarity between the word vectors representing the words. The difference between relative association is again the null hypothesis. So if we expect that the two sets of target words are as similar as the attribute words in terms of cosine similarity. So what they do is, again, they take the cosine similarity of two vectors, and they take that as analogous to the reaction time in the IAT. However, there's one problem, and this is where my thesis comes in, namely that the cosine similarity is symmetric measure. So nurse is as similar to woman as woman is to female, but that is not, however, how the IAT is set up. And namely, categorization is not a symmetric measure. So what my research does is that I developed the positive operator association test, which is also an NLP version of the IAT, but now instead of representing words as just the word embedding or the word vector, we represent words as positive operators by a collection of its hyphonyms. And we will go into what hyphonyms and positive operators are a little bit later. but we represent the target and the attribute words not as vectors but as positive operators, which are matrices in a certain space. And because we represent them as positive operators, research by Lewis in 2019 has shown that then we can use a measure of graded hyponymy as a proxy for graded categorization, which again is a lot closer to what the IIT does than a measure of similarity, which is symmetric. The null hypothesis that I use in my research is the same as the WEAT uses, and also the same as the IIT uses, namely that there's no difference in relative association between the two target sets and the attribute sets. So a hyponym of a word is, two words are in a hyponym relation, or hyponymy relation, if word A is an instance of word B. And a couple examples are that an oak is a tree, and that a programmer is an occupation. Positive operators are a special class of matrices, and Lewis has also shown that we can use that the ordering that they have on them, namely the Lerner ordering, and we can interpret that ordering as a hyponymy relation. And how exactly we do that, I will show you later. But using these hyponyms and these positive operators, we can now define this measure, namely that if we have two positive operators, A and B, of two words, we can use this measure called KE, and what this measure does is it measures the graded hyponymy between two matrices, two positive operators, which is a value between 0 and 1, sort of a graded categorization. And what does it exactly measure? Well, if in the Lerner ordering matrix A is smaller or equal to matrix B, positive operator A is smaller or equal to positive operator B, then B minus A is actually again a positive operator. And in this case we say that A is related to B in terms of KE for a value of 1. Otherwise, if it is not the case that D is a positive operator, which means that A is actually not smaller or equal to B, then we try to find this matrix E, and we determine its size. And as you can see in the diagram, so in this case, if A is not fully contained in B, then we have this sort of E that we need in order to make the equation B minus A plus this error matrix again a positive operator. And we measure the size of this error matrix in order to determine to what extent a positive operator is a hyponym of another positive operator. So how do we build these positive operators? We take the glove embedding of a certain word, and then we take the outer product of the vector with itself, which gives us a matrix, and this matrix is actually a positive operator. And then in order to represent the entire word, we take the hyponyms from a certain source. In my research I use WordNet and Microsoft Concept Graph. And we gather all the hyponyms of a certain word, and then we sum all the matrices that we build in the example above. We sum them all together, and we call this the positive operator of a word. Now that we have the positive operators of a word built with the collection of all its hyponyms, we can define how we measure the association between the target sets and the attribute word sets. So we define a function S that it takes the mean of the values of KE for all words for a word with all. So now that we have all the positive operators for target sets and attribute sets, we can define how we measure the differential association. We define a function S, and this function S measures the mean KE between a certain word in a target set between all the attributes in a certain attribute set. And then it takes the mean, so it takes the mean for a word in X with all the words in A minus the mean of X with all the words in B. And then if we have this measure, we can put that together, and we can derive the effect size of the KE by taking S for not only one word in the target set, but for all the words. And then we do the same for Y. Then we subtract the difference in mean, and we normalize. And this is then called the effect size. And this is analogous as to how the wheat test does it. And then finally we test for significance by using the one-sided p-value of the permutation test, where we take all the permutations of the target sets and see if their effect size actually comes out larger than our tested effect size, and we count all the times that it does, and that gives us a result to whether or not our results are significant. Now this table shows the results for the POAT, so the positive operator association test, compared to the IIT values and the wheat values in effect sizes. The bold values in the table highlight the values that are closest to the IIT, and in this case we built the positive operators, as I said above, using the collection of hyphonyms. And in this table you can see that the POAT actually outperforms the wheat in 3 out of 8 cases. However, the wheat still is closer to the IIT in the other 5, and you can also see that the POAT actually has a negative effect size here, meaning that the POAT recognizes an implicit bias the wrong way around. Also, it is not able to recognize an implicit bias in row number 6. And in the next table we can see also the POAT, but now we do not build the positive operators using the collection of hyphonyms, but we just use the single word embedding for the vector and build a positive operator of that. We again compare to the results of the IIT and the wheat, and the bold values again highlight the closest values to the IIT in effect size, and here we can see that the POAT actually outperforms the wheat compared to the IIT in terms of effect size. So in 6 out of 8 experiments, the POAT actually recognizes a bias which is closer to the IIT than the wheat does. And it is also able to recognize the correct bias. So as we can see from these results is that sometimes the POAT is not able to recognize the correct bias, or not even able to recognize a bias at all. And this is to do with the inconsistent way of gathering hyphonyms, because the word net that we use to gather the hyphonyms sometimes does not have an entry for the word that we want, the target word or the attribute word, and sometimes a word has a lot of hyphonyms, and sometimes a word has very few hyphonyms. And as we've seen in the results, this means that sometimes the word is not able to recognize a bias, or the bias is wrong. Also, WordNet is a human-curated database. WordNet is a human-curated database, meaning that, as we've shown, if we use human curated data or human-generated data, we can have some biases that are reflected in our models that we make of this data. And similarly, for WordNet, it is also possible that the curators of WordNet induce some kind of bias into their representation. And it is possible that this bias is also present in the POAT results. For the future work, the positive operators have been shown by Lewis to be able to sit inside a compositional framework, which means that instead of only showing that there is implicit biases between words, we can also show that there is implicit biases between words and subphrases, which could also be very interesting. And finally, and maybe the most important aspect of future research, is that, as you've seen from the results, the KE measure on single word positive operators instead of positive operators represented by the collection of hyphonyms actually performs a lot better. It would be very interesting to see why this exactly is, and it would be really interesting to see why exactly this is the case. Thank you for listening, and I hope you enjoyed the presentation, and I hope you enjoy reading through my abstract and my thesis. Thank you.